Hello, I'm Nick, and this is Today in Philosophy of History for Thursday, 21 August 2025. Possibly the most famous thought experiment in philosophy is Plato's allegory of the cave. In the allegory of the cave, which begins Book 7 of the Republic, Plato has Socrates describe to Glaucon a strange scene that will be the setting for the discussion that follows. In the classic Jowett translation, Plato sets the scene like this. Quote, "Behold, human beings living in an underground den, which has a mouth open upwards toward the light and reaching all along the den. Here they have been from their childhood and have their legs and necks chained so they cannot move and can only see before them, being prevented by the chains from turning round their heads. Above and behind them a fire is blazing at a distance, and between the fire and the prisoners there is a raised way, and you will see, if you look, a low wall built along the way, like the screen which marionette players have in front of them, over which they show the puppets." Unquote. Socrates goes on to explain how the shapes carried between the fire and the cave wall make shadows on the wall that those chained in the cave accept as the only reality that they know. It's only when someone gets free that they can turn around and see that they have what they have taken for reality all this time are mere shadows. And when they get free, they can see the shapes that have been actually casting the shadows on the wall of the cave. And Socrates goes on to describe the journey of one who was formerly chained in the cave of shadows up into the light to see the real world above, last of all being able to look at the light of the sun, since his eyes have been accustomed to darkness and it takes time to adjust to the brightness of the daylight. In setting up his thought experiment, Plato's purpose is simultaneously epistemological, metaphysical, and ethical. It's about what we can know of our true situation, what the true nature of the world is, how the quest to know the world as it truly is at the same time a moral aspiration. In Plato's metaphysics, what is truly real are the forms, and the ordinary things of this world are mere shadows of these truly real things. And this makes us, like those chained in the cave, to take shadows for being real things. In my episode on J.R. Lucas, I quoted Bertrand Russell as having written, quote, "Gödel turned out to be an unadulterated Platonist and apparently believed that an eternal naught was laid up in heaven where virtuous logicians might hope to meet it hereafter." Unquote. That's in Russell's usual tongue-in-cheek style. But what Russell meant by saying that Gödel believed that an eternal naught was laid up in heaven was that Gödel believed logical negation to be a Platonic form, and all our uses of negation are a pale reflection of the true and immutable form of negation. The philosopher who frees himself from his chains and eventually finds his way out of the cave only slowly becomes accustomed to seeing the world as it is, which for Plato means seeing the forms themselves and not the mere reflections or shadows of the forms. And when we've been delivered from the cave of shadows, only last of all can we look up the sun above the mouth of the cave, which is the form of the good, which is the most exalted of all the forms. If we return to the cave after having looked upon the form of the good, we'll be nearly blind, and those who never left the cave will be far better at seeing the shadows on the wall of the cave than they take to be the only real things that there are. Plato summarizes his thought experiment in this way, quote, "This entire allegory, I said, you may now apprehend, dear Glaucon, to the previous argument. The prison house is the world of sight. The light of the fire is the sun. and you will not misapprehend me if you interpret the journey upwards to be the ascent of the soul into the intellectual world, according to my poor belief, which at your desire I have expressed, whether rightly or wrongly, God knows. But whether true or false, my opinion is that in the world of knowledge, the idea of the good appears last of all, and is seen only with an effort, and when seen is also inferred to be the universal author of all things beautiful and right, parent of light and of the Lord of light in this visible world, and the immediate source of reason and truth in the intellectual, and that this is the power upon which he who would act rationally, either in public or private life, must have his eye fixed, unquote. To properly appreciate this, you need to read all of Book 7 of the Republic, since I'm only offering a sketch of what Plato said there. And of course, to properly appreciate Book 7 of the Republic, you have to read the rest of the book. The allegory of the cave, for example, appears within a discussion of the education of the guardians, who are the philosopher kings who rule Plato's Republic in rotation, having been trained their entire lives for this task. The allegory of the cave has been enormously influential, and philosophers have ever since formulated their own version of the cave of shadows, in which we believe ourselves to have true knowledge, but we have nevertheless been deceived in that belief. We can understand later thought experiments like Descartes' evil demon, Gilbert Harman's brain in a vat, Robert Nozick's experience machine, and Nick Bostrom's simulation hypothesis as variations on the theme of Plato's cave. Nozick's experience machine is motivated by ethics, like Plato, though Descartes, Harman, and Bostrom aren't as focused on metaphysics and ethics as was Plato, but they all explore the idea of how we know what we know, which is the central question of epistemology. These thought experiments, in turn, have inspired dozens of films, most famously The Matrix, but also The 13th Floor, Inception, Source Code, and many others. Plato's non-naturalistic conception of the world makes the allegory of the cave a reflection of the human condition. In our naturalistic age, we're less likely to see ourselves as being confined in a cave of shadows, knowing nothing of the forms that are what is truly real, but we still face limitations of knowledge, and we're often deceived in terms of what we think we know. And modern technology has given us new ways to imagine how we might be deceived, as in the brain in the vat thought experiment or the simulation hypothesis. As we have elaborated our naturalistic conception of the universe with the growth of scientific knowledge, we may be no better at metaphysics or ethics than with Plato, but we seem to have an epistemic advantage over earlier philosophers. We can look back over a long history of how science has struggled to wrest knowledge from ignorance. Our long history means we have much more experience in the formulation of knowledge, and we know by experience how easily and how often our methods for converging on knowledge can go wrong. With this experience in epistemic failure and fallacy, we're better able to avoid those epistemic pitfalls that have been a problem for us in the past. And as our knowledge of our place in the universe has gained in scope and detail, we know more about the conditions of our own knowledge. We know ourselves to be, for example, fallible biological beings subject to all manner of contingencies, both phylogenetically in the evolution of our species and ontogenetically as individuals. Our idiosyncratic existence as individuals, with all our quirks and eccentricities, is a microcosm of our idiosyncratic existence as a species. The brain we now know to be a survival machine before it's a reasoning machine, and as such, it's very good at survival and only reasons with difficulty. But knowing ourselves to be vulnerable to countless cognitive biases, we've started to catalog these cognitive biases and to interrogate our own knowledge in order to purge it of its fallacies and its failures. Our attempt to purge our reasoning of fallacies and cognitive biases is still highly imperfect, since there's still many among us who proclaim their scientific skepticism from one side of their mouth while proclaiming obvious absurdities from the other side of their mouth, but we're making a kind of progress in our acquisition of knowledge. This progress is slow and incremental and subject to setbacks, but it's still epistemic progress over the long delay. From our position as fallible contingent beings, we examine our contingent and often deceptive world in our attempt to schematize it more exhaustively in terms of our knowledge. And to this end, we not only use all our senses to derive whatever we can from the world, we also extend our senses through technology, penetrating deeper into the world than our native faculties allow for us to do. We may see ourselves as fortunate for having as much of the world revealed to us as we have in fact. This epistemic good fortune extends beyond our immediate circumstances and reaches up to the stars. I've previously quoted Hans Blumenberg from the first page of his Genesis of the Copernican World, which starts out, quote, "The combined circumstances that we live on Earth and are able to see the stars, that the conditions necessary for life do not exclude those necessary for vision, or vice versa, is a remarkably improbable one. This is because the medium in which we live is, on the one hand, just thick enough to enable us to breathe and to prevent us from being burned up by cosmic rays, while on the other hand, it is not so opaque as to absorb entirely the light of the stars and block any view of the universe. What a fragile balance between the indispensable and the sublime," unquote. Not only do we see the sun, moon, and stars in the sky, but when we see the Milky Way in a clear and dark night, we're able to, with our own eyes, see a major structure of our galaxy. And if we know where to look, we can even see other galaxies, such as the Magellanic Clouds and the Andromeda Galaxy. So from the evidence of our own senses, we can see for ourselves our place in the universe, at least in part and to a certain extent. Blumenberg, in the quote I read, is implying that it might have been otherwise. We might have evolved in a world with a thicker atmosphere that wouldn't allow us to see the stars. Given what we know now about astrobiology and habitability, it's not difficult for us to conceive of circumstances in which the conditions necessary for life do exclude those necessary for vision, and where this is the case, we would have a naturalistic equivalent of Plato's cave, in which any intelligent beings that evolved in this environment would be prevented by their circumstances from observing with their own senses their place within the universe as we do. Conditions necessary for life that exclude those necessary for vision provide us with parallels to Plato's cave formulated in terms of astrobiological possibilities for habitability, that is to say, the conditions necessary for life. There are many definitions that have been proposed for astrobiology, and one of these definitions runs as follows, quote, "Astrobiology is the study of the origin, evolution, distribution, and future of life in the universe," unquote. This definition, among others, has been used by NASA. I got it from a NASA webpage. Insofar as humanity is a part of that life studied by astrobiology on a cosmological scale, astrobiology is implicitly also about the origins, distribution, and destiny of humanity in the universe. This is a grand theme, and it's also a theme of the philosophy of history. That is to say, astrobiology is part of a naturalistic philosophy of history. It's a way to understand our history in deep time naturalistically. And in this way, astrobiology and human history are adjacent disciplines, and both have cosmology as their ultimate setting, although cosmology takes us into realms of deep time that the human mind can scarcely conceive. Today's exploration of astrobiology is undertaken in the spirit of its commonalities with history, and especially a naturalistic understanding of human history, because there's a relationship between naturalism in the philosophy of history and deep time. Naturalism yields science, and science in turn yields deep time as an extension of history. But the ultimate expression of history is due to the formal sciences, which provide us with a model to extend time even beyond the deep time of natural science. Traditional history is nested within the deep time of the natural sciences, and the deep time of the natural sciences is nested within the infinitistic time of formal history. I hope to expand on this in a future episode, but for the moment, I just mentioned it as the larger context of history in which human history is a local limiting case. In a naturalistic philosophy of history, human history is one of many possible histories. And even if human beings are the only intelligent life in the universe, there's still a history of intelligence in the universe. It's just a history where the local limiting case is the only case. Contextualizing human history in an astrobiological context gives us a way to understand history in terms of fundamental concepts of natural science. Astrobiology has grown rapidly since its inception, and as it's grown, its foundational concepts have developed, becoming more sophisticated and more adequate to what it attempts to explain. One of these foundational concepts is habitability, and the concept of habitability has changed as astrobiology has developed. Habitability was initially understood to be about understanding what makes life on Earth possible, and it understood the possibility of life elsewhere in the universe only in terms of close analogs of Earth. But as it turns out, there are a lot of potentially habitable niches in and around our solar system in all kinds of unlikely places, such as deep craters on Mercury or the clouds of Venus. Presumably, other planetary systems also have a variety of habitable niches, and the distribution of life across these niches could be different from the distribution of life among habitable niches in our solar system. As we saw with the NASA astrobiology definition I quoted earlier, astrobiology studies the origin, evolution, distribution, and future of life, which implies that all of these things, origins, evolution, distribution, and future, may exhibit a range of permutations in other planetary systems. One of the most interesting developments in habitability has been the realization of the potential habitability of subsurface oceans in icy moons and dwarf planets beyond the frost line. This isn't just about other planetary systems, since our own outer solar system seems to have several subsurface ocean worlds. The Jovian moons, Europa, Ganymede, and Callisto, the Saturnian moons, Enceladus, Titan, and Mimas, Neptune's moon Triton, and dwarf planets like Pluto and Ceres may have subsurface oceans, or in the case of Ceres, brine pockets, that is to say, not a planetary scale ocean, but still a lot of water. We detect subsurface oceans by geophysical signatures like a magnetic field, gravity, planet shape, and longitudinal librations, that is to say, a wobble in the planet or planetesimal's rotation. Other subsurface ocean signatures include surface geology, such as cryovolcanism, plumes, fractures, and ridges on the surface, surface composition, thermal and atmospheric signatures, and chemical and isotopic signatures. So we have many kinds of evidence that point to subsurface oceans. This is now called planetary oceanography, astrooceanography, or exooceanography, but it's all very recent. It wasn't until 1979, when the Voyager spacecraft flew past Jupiter, that the idea of subsurface liquid water oceans started to gain traction. What caught everyone's attention at the time and made the front covers of magazines were the volcanic eruptions on Io. But this was a heads up for planetary scientists to think about the heating that gravitational tidal forces can cause. Given heating from gravitational tidal forces, a moon largely composed of water ice around a small rocky core could have liquid water between its core and its icy outer crust. In late 1995, when the Galileo spacecraft arrived at Jupiter, it took readings of Europa's magnetic field, providing further evidence of a salty and conductive subsurface ocean. So planetary oceanography only really became a thing in the 21st century, and it's changed the way we think about habitability. The prior paradigm of habitability was pretty narrowly constrained by a habitable belt around a star, and then a planet of the right size and composition being in this habitable belt that would enable or facilitate liquid water on its surface. The possibility of subsurface ocean habitability transforms the distribution of habitability. A planetary system might possibly have an Earth twin in its habitable zone, while it also may not. But it's very likely that it has a great many icy moons and dwarf planets beyond its frost line, where volatile compounds like water condense into solids, facilitating their accretion into planetesimals. And there's a lot more that I could say about the frost line, also called the snow line or the ice line, and the development of series of planet formation, but I'm not going to talk about that today. There may be hundreds of billions of subsurface ocean worlds in the Milky Way galaxy, and a larger galaxy like Andromeda would have even more of them than the Milky Way. So we're talking about trillions of these kind of worlds just within our local galactic cluster. This bonanza of habitable niches obviously raises the question of whether life originated in any of these subsurface ocean habitable niches, and if so, whether any of this life evolved intelligence. If there is intelligence under the ice of any subsurface ocean anywhere in the universe, that intelligent life is our peer. That is to say, our peer in the sense of being a biological being that has evolved intelligence and so represents a certain number of thresholds along the ladder of emergent complexity, roughly equivalent to our own threshold of complexity. These subsurface ocean peers of ours would be the result of a different evolutionary pathway, but still an evolutionary pathway nevertheless, a peer evolutionary process with a peer outcome. But if any intelligence evolved in the subsurface ocean worlds, it would, in a sense, inhabit a very different world from ours, with no sky and no way to view the cosmos. No moon, no planets, no stars, no constellations. Such beings, without a view of the stars, would have no way to observe their place within the world as we do. Even if they could overcome the technological disability of being aquatic, and thus without a metallurgical technology, their intellectual disability from not being able to observe the universe might be more significant yet. They would be like the unfortunate denizens of Plato's cave, forever doomed to see only shadows on the wall and not the things themselves. So that brings us to the question I've used as the title for this episode. Are subsurface ocean worlds Plato's cave? Are there intelligences trapped in subsurface oceans, and they not only can't escape, but they can't even see beyond their ocean? We can even strengthen the isolation of any life in subsurface ocean worlds by observing, that the subsurface ocean worlds orbiting Jupiter are subjected to intense radiation on their surfaces. The ice itself, in most cases many kilometers thick, would shield any subsurface ocean biosphere from radiation. But that life could never emerge from a subsurface biosphere because of the strength of the radiation. So an intelligence in a subsurface ocean could be trapped under kilometers of ice surrounded by powerfully radioactive plasma. That's like being hermetically sealed into Plato's cave with no way out. I'm going to set aside the question of whether life could originate in a subsurface ocean world because we can't engage in our thought experiment today without allowing this to be the case. There's been some speculation on this question and is related to the problem of whether life could originate on a water world. And both subsurface ocean worlds and water worlds share the problem of whether, given life, intelligent life can evolve, and given intelligence, whether technology is possible. One response to the Fermi paradox is that most life occurs in water world, and this explains why we've detected no radio transmissions from other civilizations. I'm not advocating this as a solution to the Fermi paradox, but it has been put forward, so I note it here. But we need to make a distinction between water worlds, which are habitable zone planets are almost entirely covered by an ocean, which makes them a subset of traditionally habitable worlds, and subsurface ocean worlds, which are icy moons and dwarf planets beyond the frost line. Both pose problems for intelligent life and civilization, but intelligence on a water world wouldn't be sealed into a cave, and subsurface ocean worlds are likely to be far more plentiful in the universe, so they pose the problem of a naturalistic equivalent to Plato's cave in a particularly robust form. Even if we were to hold that an intelligent species on a water world couldn't build technologies or have a civilization, they could still see the stars on clear nights, and that means they could develop some kind of observation-based astronomy. One argument that water worlds wouldn't develop life and therefore couldn't have developed intelligence is that water worlds lack the particular biogeochemical cycles necessary to the evolution of large and complex life, though there are also those who argue on the other side of this question. The 2018 paper, The Ice Cap Zone, a Unique Habitable Zone for Ocean Worlds by Ramses Ramirez and Amit Levy, postulate a role for subpolar sea ice in the regulation of CO2, which on Earth is regulated by the carbonate silicate cycle. The problem, of course, is the same problem we have with conceptualizing life that is radically different from life as we know it. Just as we only know one biological regime, that of Earth, we only know one biogeochemical regime, again, that of Earth. The biogeochemical cycles of water worlds, if any, will be distinct from the biogeochemical cycles of planets like Earth, with both continents and oceans, and the biogeochemical cycles of subsurface ocean worlds will again be distinct from the biogeochemical cycles of water worlds. Another argument that has been frequently made against intelligence on water worlds is that an intelligent being in an aquatic environment couldn't develop a technology, or more narrowly, it couldn't develop a technology based on the domestication of fire. This is a problem shared by water worlds, which, as I said, are a subset of traditional habitable zone worlds, and subsurface ocean worlds, which are our focus today. If you've ever watched any of the episodes of the Primitive Technology YouTube channel, you'll have some appreciation of the role of fire in elementary industrial processes. A tradition of technology that had no use of fire would be radically different from the development of technology as human beings have known it, which has been pervasively dependent on the use of fire. In my episode on Kardashev, I cited a 2017 paper by Olivia P. Judson, The Energy Expansions of Evolution, in which the author identifies what she calls 5 energetic epochs consisting of geochemical energy, sunlight, oxygen, flesh, and fire. The last of these, fire, initiates a new energy epoch, according to Judson, that has unfolded in 2 phases. Quote, "The first phase began with the evolution of a fire creature. This creature, a member of the genus Homo, began to control the use of fire, deliberately setting fires alight and using fire for cooking. Exactly when cooking became remains controversial, with possible dates ranging from 1.5 million years to 0.4 million years.". So much for the first phase. And Judson continues, quote, The second phase of fire as an energy source is even more recent, but the onset is nevertheless difficult to pinpoint. Does it start with the use of fire to manufacture labor-saving tools? With the smelting of iron, something otherwise energetically impossible? With the burning of fossil fuels such as coal to generate heat and light? With the invention of the internal combustion engine? Or with the discovery of the Haber-Bosch process for fixing nitrogen, which in 1925, Alfred Lotka described as the start of a new cosmic epoch, unquote. So Judson calls human beings a fire creature. And in the subsurface ocean world, there could be no fire creature, and therefore, there would be no use of fire to manufacture tools, no smelting of iron, no burning of fossil fuels, and no Haber-Bosch process. These technologies that harness fire have been poetically called the Promethean protocol by the Italian philosopher of technology, Fabio Grignenti. Grignenti wrote, quote, ceramics and steelworking can be seen as applications of one and the same general operating framework that, since it rotates around the use of fire, we might call the Promethean protocol, unquote. Is the Promethean protocol a necessary condition for the development of technology, or does it rather mark a bifurcation in the development of any intelligent species, where this intelligence either follows the Promethean protocol or instead follows what we might call the Poseidonian protocol? The claim that intelligent beings on a water world or in a subsurface ocean world couldn't develop a technology could be interpreted as the claim that there is one and only one technological clade, and that is the Promethean protocol, which is denied to aquatic intelligence. To put it in Judson's term, fire initiates the Promethean protocol and is iterated in the development of the Promethean protocol. Without fire, there is no Promethean protocol, hence no development of technology, meaning that technological development is tightly constrained by the Promethean protocol. There's no technology outside of that. So far, I've been framing this in terms of technology, but the problem can also be framed in terms of civilization. The transformation of society under selection pressures brought to bear by the widespread adoption of certain technologies has begotten human civilization. The Promethean protocol, reinterpreted as a thesis in the theory of civilization, holds that fire lies at the basis of a sequence of technology, here called the Promethean protocol, that constituted an anthropogenic selection pressure on human societies, and human civilization is a result of that selection pressure. We find an elaboration of this, in a sense, in Johann Holtzblum's 1992 book, Civilization and Fire. And yes, I don't know how to correctly pronounce the guttural G at the beginning of a Dutch name, but hopefully you get my drift. Holtzblum follows the lead of Norbert Elias, who studied civilization from the perspective of sociology. I mention this because it offers an interesting contrast to others I've profiled, like V. Gordon Childe, who studied civilization from the perspective of archaeology, and Philip Bagby, who studied civilization from the perspective of anthropology. Norbert Elias wrote a book titled The Civilizing Process, and Holtzblum views the control of fire from the perspective of a civilizing process using several of the analytical tools formulated by Elias. On the control of fire, Holtzblum writes, quote, I will look at the way it has evolved as an integral part of human society. That human beings have learned to handle fire at all I regard as the outcome of socio-cultural development. The possession of fire has made human societies more productive and more formidable, but has also increased their capacity for destruction and made them more vulnerable. As a part of the apparatus by which people controlled nature, the control of fire has always been and always will continue to be enveloped in social control and self-control, unquote. Holtzbloom doesn't pursue a reductionist line of reasoning in Fire and Civilization, according to which fire is necessary to human civilization, but he uses the more guarded formulation that control of fire, quote, can serve as a focus for studying the process of civilization itself, unquote. While his formulations on the control of fire in relation to civilization are reasonably circumspect, on another level, Holtzbloom jumps the shark as when he writes, quote, human history or prehistory offers not a single example of an entirely normless group of a society still completely uncivilized, unquote. Here again, he's following Norbert Elias, whom he cites as arguing that it would be impossible to isolate a starting point in the civilizing process. This might seem innocuous, innocuous, but it's related to developments in the study of civilization that, I think, have contributed to the stagnation of the study of civilization and its failure to converge on a paradigm that would make a scientific research program in the study of civilization possible. There's a sense in which it's understandable that Holtzbloom would hold this view given his interest in the role of fire. The paper I cited earlier by Judson notes that, quote, exactly when cooking began remains controversial, with possible dates ranging from 1.5 million years to 0.4 million years, unquote. This extends the chronology of civilization, as Holtzbloom would have it, by at least 2 orders of magnitude, from 5,000 years to 500,000 years. Now, 500,000 years is a long time, longer than Homo sapiens has existed, but it still only kicks the can down the road on the origins of civilization. And admittedly, it kicks the can way down the road, but the problem still comes up, especially at the scales of time that I often talk about. Do we really want to say that civilization began before human beings in the narrow sense of Homo sapiens existed? There's a problem here, and Russian anthropologist Nikolai Craden has put the problem succinctly. Quote, there is still no agreement concerning the objective criteria on which to base classification. There is no agreement concerning the number of civilizations up to and including the point at which every ethnic group can be given recognition as a civilization, unquote. If any ethnic group can be recognized as a civilization, then civilization has ceased to mean anything at all. It doesn't distinguish any one society from any other. So while Holtzbloom, following Elias, resists a reductionist account of civilization's dependence on fire, he also, however, can't distinguish a civilization from any other society. And these other societies could include societies that haven't domesticated fire, whether prehistorical human societies or non-human societies, as in the case of an intelligence evolved in a subsurface ocean world. This results in a muddle that doesn't help us to understand the possibilities and challenges of technology for an aquatic species in a subsurface ocean world. Others have been less circumspect and more explicit on the necessity of fire for technology, and that the absence of fire means not only the absence of technology, but also the absence of intelligence that could domesticate fire. The famous entomology E.O. Wilson in The Social Conquest of Earth wrote, quote, the use of fire was forever denied to insects and other terrestrial invertebrates. They were physically too small to ignite tinder or carry a flaming object without becoming part of the fuel. It was, of course, also denied aquatic animals, regardless of size or prior degree of intelligence of whatever nature, unquote. E.O. Wilson goes on to insist categorically that pure intelligence cannot evolve in an exclusively aquatic environment. Quote, A Homo sapiens level of intelligence can arise only on land, whether here on Earth or on any other conceivable planet, unquote. There are a lot of assumptions built into the claims of both Hutzblum and Wilson, and the failure of imagination to see the possibilities for an alternative technology not derived from fire carries a heavy burden. Some of the assumptions involved here have been made explicit in relation to subsurface ocean world by Alan Stern in a one-page conference report of 2017, an answer to Fermi-Mead's paradox in the prevalence of ocean worlds. Stern distinguishes three kinds of what he calls water-ocean worlds, which he abbreviates WOW, namely type 1, solid bodies with external ocean, that's like Earth; type 2, icy satellites and small planets with interior ocean, that's what I've been calling subsurface ocean world; type 3, gas giant planets like Uranus and Neptune with high pressure interior ocean. And he asserts that type 2 water ocean worlds, icy moons and dwarf planets, quote, the great majority of worlds with biology and civilizations are interior ocean worlds cut off from communication because they're inside of their host world, unquote. Unlike those who have questioned the habitability of water worlds, I should say, Stern argues that subsurface ocean worlds are likely to be clement to life because of environmental independence to stellar type, multiplicity, distance, and environmental stability. And his conclusion apropos the Fermi paradox is this, quote, where are they? The answer may simply be at home in their type 2 water ocean worlds, where they either cannot communicate or are simply not aware of other worlds, that other worlds exist or could have communicable civilizations, unquote. Stern emphasizes both the difficulty of intelligence in subsurface ocean world communicating or traveling beyond their environment of evolutionary adaptation, and the likely lack of interest or comprehension for intelligence in any other kind of environment, like our environment, which Stern calls a type 1 water ocean world. Given that we have an interest and at least a limited understanding of the possibility of intelligence evolving in environments radically different from our own, I suspect that intelligence in subsurface ocean worlds would also be able to make this leap. And if life and intelligence is common in such environments, the environmental stability that Stern notes would mean such an intelligence would have plenty of time to think it over. The same observation made by Ray P. Norris in his 2000 paper, How Old is E.T., such that any contact we are able to make by these beings would be with an intelligence millions or billions of years in advance of us, also holds for intelligence in subsurface ocean world that we might contact. An intelligence in the subsurface ocean world might have had millions of years to think about its evolutionary origins and what's possible, and the technological hurdles ought to be of little moment to such an advanced intelligence. The fact that any intelligence in a subsurface ocean world would face a situation not unlike being sealed into Plato's cave clearly presents obstacles to observation, and Stern notes these. But an obstacle is also a challenge in the Toynbean sense, and a challenge can be met with a response. Human beings have faced our own challenges in trying to observe and to understand the universe of which we are a part. From our own experience of plumbing the depths of the universe from a planet orbiting a star in one of the spiral arms of the Milky Way galaxy, human beings have shown remarkable cleverness in deriving counterintuitive conclusions from the evidence we could observe. When I study the history of human discovery of the dimensions of our universe, I'm often astonished by the imaginative resources that human beings have brought to the problems of the observation of the visible universe. Because of the distances we are able to observe by looking into the night sky, long before we had the instruments that would make it possible to precision engineer after the Industrial Revolution, it was possible to measure the speed of light. Once Galileo had discovered the moons of Jupiter, it didn't take long before anomalies were noticed in their timing, which is the result of Earth and Jupiter sometimes being closer together and sometimes being farther apart because of the distances involved. Working in Paris at the time, Ole Christensen Romer was the first person to measure the speed of light by scientific means. He observed the eclipses of the moons of Jupiter and discovered periodic anomalies in the timing of their eclipses. Because we could observe the heaven, we could determine that light had a finite velocity before we could build an instrument capable of measuring the speed of light. Another way to put this is that we use the entire solar system as an instrument for the observation of astronomical bodies. And now, at present, before we can build an instrument that can identify dark matter, if there is indeed any dark matter, which may turn out to be the phlogiston or the luminiferous ether of our time, we can observe the rotation of galaxies and see for ourselves that the outer edges rotate as rapidly as the inner edge, from which we can deduce that there are forces at work for which we cannot account by present physical theory and cosmology. Without the scale of observations made possible by our view of the stars, the history of science would not be what it is. So discovering the nature of the universe and our place within it was no cakewalk for humanity. And we assume it wouldn't be a cakewalk for any intelligent observer. But the question at hand is whether our view of the stars has given us a decisive advantage in science and technology. An intelligent being in a subsurface ocean world could also be clever about its observation and learn quite a bit about its world and its place in the universe. Travel within the global ocean would reveal to them that they could eventually return to their starting point, no matter in what direction they departed from their point of origin. They would know from personal experience that their ocean was spherical, finite, and unbounded. Perhaps topology would develop before plane geometry. If this were the case, the sequence of the development of the sciences would be different, just as the sequence of the development of technology would be different, but not necessarily absent. But for all the disabilities that would be native to subsurface ocean world intelligence, there might also be some unexpected advantages. There's a sense in which the environment of a subsurface ocean world not only doesn't limit an inhabitant's knowledge of the universe, but actually facilitates and possibly extends that knowledge. A subsurface ocean world would effectively be a planetary scale detection instrument for gravitational interactions, which, if measured with precision, could reveal the structure of an entire planetary system. A planetary core surrounded by liquid water and sealed within an icy crust would register subtle variations in distance between core and crust. The distance from the core of a subsurface ocean world to the underside of the surface ice would vary with its own orbit of its gas giant companion, if it had one, and according to every orbit of its companion, as well as seasonally, and possibly also according to its own day or the day of its companion planet, as well as any other moons in that system. The more precisely such measurements could be made, and the more precisely their periodization could be fixed, the more this data could be made to paint a picture of the universe beyond the subsurface ocean. It would be a challenge to measure this distance precision, but would it be impossible? There would need to be methods for measuring time and space. The spatial measurements would be straightforward, even if technically challenging. The measurement of time might pose a problem. Given that many aquatic species on Earth use sonar, an intelligent species in the subsurface ocean world might also use sonar to measure distance. But as I said, timekeeping might be more of a challenge. Most human timekeeping has its origins in astronomical observations with sundials during the day and the wheeling of the stars overhead at night. Water clocks were another early timekeeping technology, also not possible in a subsurface ocean world. But just as we have used astronomical periodicities to measure time, a subsurface ocean world might well have astronomically induced periodicities in its environment that could also be used for time measurement. The chief disability might be in making the breakthrough of conceptualizing the world as a planet among planets. But once that breakthrough is made, every measurement of the gravitationally induced changes to their ocean environment would be interpretable in this framework. Given the conceptual breakthrough, things would fall into place as our own understanding of cosmology fell into place after Copernicus, and our understanding of biology fell into place after Darwin. I mentioned Darwin in this connection because of a comment he made that's relevant to this. Quote, "Innumerable well-observed facts were stored in the minds of naturalists, ready to take their proper places as soon as any theory which would receive them was sufficiently explained," unquote. This unfolded slower with cosmology than with biology, but it's been a similar process of observed facts taking their place within a theory that would receive them. The measurements of the interior of the subsurface ocean world are not possible for us as surface-dwelling intelligent beings, and we might well consider ourselves observationally disadvantaged for not having this available to us, much as we might regret not having some given sensory modality that could have given us further observational opportunity. The particular, if not peculiar, sensory endowment of a given organism and the picture of the world yielded by this sensory endowment was called Umwelt by Jakob von Uexküll. Uexküll's Umwelt concept was adopted and adapted by Ed Yong in his 2022 book, An Immense World, How Animal Senses Reveal the Hidden Realms Around Us, which discusses in great detail the differing Umwelten of various species in the terrestrial biosphere. And it's a wonderful book, by the way. I highly recommend it. In other contexts, Umwelt is translated as environment, but this doesn't seem adequate to capture what Uexküll was getting at. Umwelt was extensively used by Husserl, who was a close contemporary of Uexküll, and again, Husserl's usage isn't exactly captured by the English translation of environment, and some Husserl's translators have rendered it as surrounding world. Dorian Cairns, in his Guide for Translating Husserl, suggests this translation, specifically warning against Umwelt as either environment or milieu, since the reference to world, he says, should be retained. It's also interesting to note in this connection that both Husserl and Uexküll were interested in time consciousness, and this is immediately relevant to the problem of a subsurface ocean being establishing a system of timekeeping sufficiently precise to serve as the basis of controlled observations. After observing how a magnifying glass changes our perception of the surface of a leaf, Uexküll wrote, quote, "The magnification by the lens depends on small sections of the field of vision being perceived by more optical cones of the retina than in normal vision. If, for instance, I project the image of a horse chestnut leaf on the visual surface of my retina, which normally would hold the entire tree, the tree itself will disappear from the field of view. But that would not happen if I could give to my retina a correspondingly large number of rods and cones. Then the whole section of space represented by the chestnut leaf would remain equally large in proportion to the whole optical surface, but it would include now as much detail as previously the whole tree did, and the tree itself would acquire a corresponding increase in detail," unquote. And after discussing this visual version, Uxko then gives a parallel formation for time. Quote, the duration of the moment stands in close relation to the number of places and to the length of the direction steps, and this relation again depends on the power of the mind to form an estimate of the world, unquote. The perception of time at a much higher degree of fidelity than the human rate of conscious awareness might enable ways of measuring time not available to us in a fine-grained perception of time that we don't possess. Could there be some temporal baseline other than astronomical periodicity? And if some intelligence were to render observations of astronomical periodicity in terms of some other temporal baseline, would that alter their observations or the science they construct upon their observations? One lesson at least we can construct by drawing on Uxko's conception of an Umwelt is that every Umwelt is the potential basis for the construction of scientific knowledge, though it also seems to be the case that some Umwelten will be more adequate to this task than others. But the other side of the coin from particular sensory endowments are the observational opportunities of a given environment. Again, we can probably distinguish environments more adequate to observation than others, as Blumenberg attempted to distinguish when he observed that Earth is not only suitable for life, but also for astronomical observation. As we've seen in the subsurface ocean world, the observational opportunities are radically different from that of worlds with surface life and transparent atmospheres, but there are still observational opportunities. These observational opportunities are as different from observing the night sky as an aquatic intelligence would be different from an terrestrial intelligence, but each observational opportunity has a certain naturalness for the kind of organism involved. For scientific knowledge to be formulated, there needs to be a coupling of Umwelt with environment that allows for observation adequate for the construction of scientific knowledge. Again, some of these couplings will be more adequate than others, and all will have limitations, as indeed our observations of the cosmos have limitations. Given that subsurface ocean intelligence might come to understand its cosmos no less than we do, perhaps the appropriate question is not whether we're living in Plato's cave, but rather how large Plato's cave may be. Plato's cave could, for example, be as large as the Hubble sphere. Leonard Susskind wrote in The Black Hole War, My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics, quote, each of us is surrounded by a cosmic horizon, a sphere where things are receding with the speed of light, and no signal can reach us from beyond that horizon. When a star passes the point of no return, it is gone forever. Far out at almost 15 billion light years, our cosmic horizon is swallowing galaxies, stars, and probably even life. It is as if we all live in our own private inside-out black hole, unquote. If the universe is infinite beyond its visible extent within our cosmological horizon, no observation can demonstrate this. Being ourselves finite, we can only make a finite number of observations of finite extent. Given that any finite extent falls infinitely short of any infinite extent, something that Aristotle called the annihilation of the finite by the infinite, the finite extent of our universe, which is vast compared to us, would be as nothing compared to an infinite universe. There's another interesting perspective on this and the limits of observational cosmology in the 2007 paper, The Return of a Static Universe and the End of Cosmology by Lawrence M. Krauss and Robert J. Scherer. Krauss and Scherer argue that due to the accelerating expansion of the universe, all galactic clusters except for the local cluster will pass over the cosmological horizon, leaving us in an apparently static universe without expansion, and the observational pillars of the Big Bang cosmology will no longer be visible. Science would at that time not be able to reconstruct the history of the universe as we know it today. Like Hans Blumenberg, whom I've quoted remarking on the coincidence of life on Earth and our ability to view the stars, Krauss and Scherer expressed their thesis also as a magnificent coincidence. Quote, "The remarkable cosmic coincidence that we happen to live at the only time in the history of the universe when the magnitude of dark energy and dark matter densities are comparable has been a source of great current speculation, leading to a resurgence of interest in possible anthropic arguments limiting the value of the vacuum energy. But this coincidence endows our current epoch with another special feature, namely that we can actually infer both the existence of the cosmological expansion and the existence of dark energy. Thus, we live in a very special time in the evolution of the universe, the time at which we can observationally verify that we live in a very special time in the history of the universe." Unquote. In their Scientific American article, The End of Cosmology, An Accelerating Universe Wipes Out Traces of Its Own Origins, Krauss and Scherer are a little more speculative, arguing, quote, "Although we are certainly fortunate to live at a time when the observational pillars of the Big Bang are all detectable, we can easily envisage that other fundamental aspects of the universe are unobservable today. What have we already lost? Rather than being self-satisfied, we should feel humble. Perhaps someday we will find that our current careful and apparently complete understanding of the universe is seriously wanting." Unquote. There's another interesting, albeit subtle, framing by Krauss and Scherer in this article. In describing what they call the end of cosmology and the return of a static universe, they are equating cosmology as astrophysical events and processes at the largest conceivable scale with cosmology as a scientific discipline practiced by human beings or other intelligent observers. In their Scientific American article, they explicitly write about civilizations maintaining archives over billions of years as a response to observational conditions. Quote, "Some civilizations might hold on to deep historical archives, and this very article might appear in one if it can survive billions of years of wars, supernovae, black holes, and countless other perils. Whether they believe it has another question, whether they will believe it is another question. Civilizations that lack such archives might be doomed to remain forever ignorant of the Big Bang." Unquote. The idea that observational cosmology can no longer yield the three pillars of Big Bang cosmology means the end of cosmology is the cosmological equivalent of the commonly expressed distinction between history as res gestae and history as historia rerum gestarum. Moreover, they drop hints about the anthropic cosmological principle as a way to address what they see as a problem arising from their conflation. Should we postulate an anthropic historical principle according to which, in its strong form, history is a necessary consequence of human existence? Implicitly, I think many historians do hold a view something like this, though they don't call it an anthropic principle. And some would make this definitive of history, that is, that it must be about human beings. That leaves us with the problems of deep time and natural history into which human history is telescoped. Cosmological actuality would not be changed by the changing circumstances of observation. But there's an opportunity here both to expand our conception of history and to comprehend cosmological deep time within a recognizable historical framework. Since the proper generality with which we should understand history is a cosmological context, and in this cosmological context, we aren't concerned exclusively with human history, as would be implied by positing an anthropic historical principle. We would want rather an historical principle that's non-anthropocentric. The possibility of intelligence in a subsurface ocean world and how it might come to understand the universe on its own terms would be another history in the universe, a peer history of a pure intelligence. Its principle of history wouldn't be anthropic, but it would be the historical principle of a pure intelligence, and therefore a pure historical principle. Both human history according to an anthropic historical principle and the history of some pure intelligence according to a pure intelligence historical principle would fall under a more general principle according to which cosmological history is a function of the intelligent observers, regardless of whether the observer is human. A lot of work would be required to flesh out this idea, but I think it would be an interesting exercise and ultimately worth the effort. There's much more that could be said about everything I mentioned today, but that's where I'll end it for the moment. Thanks for listening.